you're going to want to memorize the result from this one because it pops up fairly often, you know, things like 1 over x squared plus 9 or 1 over x squared plus 16 or something like that. So if we're trying to think about partial fractions, there's not really a good way to do this using a partial fraction because you can't factor out the denominator, right? X squared plus a squared is a sum of squares. There's no way to factor that using real numbers. So we'll have to go back and use one of our old techniques. And so I think the easiest technique for us to use for this is to just go through and use the inverse trig substitutions like we had before. So what trig substitution would we use for this one? Yeah, tangent, exactly. So we'll let x equal a tangent theta, which gives us dx is equal to a secant squared theta d theta. And we end up with an integral of a secant squared theta d theta over a squared tangent squared theta plus a squared. Everybody good with that? Okay. We can factor the a squared out of the denominator, which leaves us with a over a squared, which should just be a 1 over a. And since a is a constant, we can put that out in front. So 1 over a times the integral of secant squared theta d theta over, and when we factor out the a squared, this is tangent squared theta plus 1, which is also secant squared. So we got secant squared theta d theta over secant squared theta. Everybody good there? Hopefully. And then we'll cancel off the secant squareds and just have an integral of d theta, or 1 d theta. And what's the integral of d theta? It ought to just be theta, right? So we have 1 over a times theta plus our constant. And what is theta equal to? Divide by the a and then take the inverse tangent, right? The inverse tangent of x over a. So anytime you have 1 over x squared plus a squared, it ought to be integrated as 1 over a inverse tangent of x over a plus a constant. And you'll want to memorize that because that's going to pop up often enough that we'll want to use it, especially when we're doing these partial fraction decomposition ones. Everybody good with that? All right. So let's take a look here. 2x squared minus x plus 4 over x cubed plus 4x. So first question is it a rational function? Yes. Is there a simple u substitution that we can use? Can I substitute out that denominator? And is it easy to get the numerator if I do that? Yeah, it doesn't look like it. Second question is the degree of the numerator more than or equal to the degree of the denominator? Again, no, so we don't want to divide, so we just need to factor that denominator out. Adrian, you sent me a message about if we're memorizing these ones, can you just use them on the AP test? Yes, you don't need to solve them manually on the AP test for any of these ones I have you memorize. Just know those integrals and be able to apply them. All right, so no easy u sub and no reason to do a long division. So let's rewrite this with the denominator factored. So this ought to be an integral of 2x squared minus x plus 4 over x times x squared plus 4. And we'll note right away that x squared plus 4 is that sum of squares that we were just dealing with. It can't be factored any further. So this is the first time that we've got one of these partial fraction ones where all the factors in the denominator are not linear pieces. So we have an irreducible quadratic factor in the denominator. Everybody see that? Everybody good with that? I hope. So we're going to use a similar process here, but the partial fraction decomposition looks a little bit different. So, it's going to start off essentially the same. 2x squared minus x plus 4 over our x times x squared plus 4 is equal to, well, the linear factor gets a constant above it, but the irreducible quadratic factor should have a linear factor above it. So we should have a bx plus c. And the reason why that is because we want to be able to get squareds up here, but nothing more than squared. So we can go up to a linear factor. Now, it's possible that the b value in some cases might end up being 0 and you don't have a linear factor up there. And that's okay. But we need to put it up there just in case there is a linear piece to it. Okay. Everybody good with that? So anytime you have an irreducible quadratic factor, the numerator of it in partial fraction decomposition has to be linear, bx plus c. All right, so now we'll just get our common denominator, and we're going to cancel out all those denominators. So the a over x needs an x squared plus 4, so that'll be a times x squared plus 4. And the bx plus c needs an x, so that'll be bx plus c times x. Everybody good there? And we got 2x squared minus x plus 4 equals ax squared plus 4a plus bx squared plus cx. Any issues with that? Everybody following along, no problem. Okay, luckily the system of equations that we're going to write here is going to be really easy to solve. So we have 2x squareds, and we have ax squareds and bx squared, so 2 equals a plus b. We have negative 1 x's, and over here we just have c x's. So negative 1 is c, that one's already done. And here we have 4 as our constant, and that equals 4a. So that ought to tell us that a is equal to 1. So we've already got 2 of them. The other one comes from here. We should also know that 2 equals 1 plus b, or b equals 1. Everybody good with that so far? Okay, perfect. So let's get a new page to rewrite our integral. This integral ends up being the integral of 1 over x, right? Because a was 1. And then plus x minus 1 over x squared plus 4 dx. Everybody good with that? Just plugging in your a equals 1, b equals 1, c equals negative 1 values. Okay, so first part of that, 1 over x is super easy, right? This just becomes natural log absolute value of x. And then the second part of it, the x minus 1 over x squared plus 4 is a little bit of an issue. We know how to deal with the x squared plus 4 if it was just a constant up in the numerator, but it's not just a constant. So what can we do with x minus 1 over x squared plus 4 to integrate it? Okay, so we could do a u substitution with it, Nick, and we're going to, but we got to do something first. We don't have to do something first, but we can make our lives a lot easier if we do something with it first. So what can we do with it before we do the u sub? Yeah, so we want to split it into 2 fractions first, and we can take the x over the x squared plus 4 as 1. And Nick, that one's a nice easy u sub, right? And then minus the integral of 1 over x squared plus 4. And now that's a nice one that we just dealt with on the previous problem, right? So for our u sub here, u is going to equal x squared plus 4. So du is going to be 2x dx, which means we'll need a 1/2 out in front of the integral. And we should be able to see then that this becomes natural log absolute value of x plus 1/2 of the integral of du over u. And what is the integral of du over u? It's just natural log absolute value of that u. And then over here, this one should become minus, and then what's our a value? Our a value ought to be the square root of 4, right? That'll be 2. So minus 1/2 the inverse tangent of x over 2, plus your constant. Good or no? And if you don't feel like writing the absolute values around that natural log absolute value x squared plus 4, that's fine, because x squared plus 4 is always positive, so it's a little redundant. So if you put parentheses there, that's fine. But make sure you got the absolute value on the just x1 for sure. Any questions or issues with that? All right, let's do another one, although I'm not sure why there's a blank page there. All right, let's do this one. What should we do to begin this one? First, look for an easy u sub. Is there an easy u sub there? Doesn't look like one. And then is the degree of the numerator greater than or equal to the degree of the denominator? Yep, so let's divide it out first. Okay, so we've got 4x squared minus 4x plus 3. And how many times does 4x squared go into 4x squared? Just once, right? So the long division on this is actually quite simple. Subtract these. -3 minus -4 is 1x. And then 2 minus 3 is -1. Everybody good there? And we end up with this as our new integral. Okay. First piece of that's really easy to deal with, right? Integral of the 1. The integral of the 1 is just x. So we got x plus the integral of x minus 1 over this whole mess, 4x squared minus 4x plus 3. Anybody have a good idea on how we're going to deal with that 4x squared minus 4x plus 3? Does it factor nicely? Okay, so 2x plus 1 and 2x minus 3. You guys agree that it factors to that? I don't think so. That's minus 3. Anybody else see a good factorization? I don't know why you did that, Nick. That's a good question. It'd be really cool if it factored, right? If it factored nicely. But we should know that it doesn't factor nicely, because if you look at the discriminant of it, b squared minus 4ac, that's 16 minus 48, which is negative. So clearly there's no real solutions to that, which means it's not going to factor cleanly using whole numbers, or even using real numbers at all. So we got to deal with this in some other way. So let's think about this idea of the a squared plus x squared, or x squared plus a squared, that we've had previously in the denominator, the last couple. Yep, Madhavi, that's right. We're going to complete the square with it. So 4x squared minus 4x plus what is a perfect square? We're not going to really go through the full completing the square process, but if that c term was what, would this be a perfect square? If instead of it being a plus 3, it was a plus what would make that a perfect square? If instead of being a plus 3, it was a plus 1, wouldn't that be a perfect square? Wouldn't that be 2x minus 1 squared? And then we'd still have a plus 2 attached to the end of it. Everybody okay with that? Rewriting it like that? All right, and how is that helpful to us? Well, if we go in here, we've now got x, don't forget the x that you had, plus the integral of x minus 1 over, now it's 2x minus 1 squared plus 2. And how's that going to help us out? What can we do with that? If we do a u sub here with u equal to 2x minus 1, then what's du? Du ought to be 2 dx. So if I were to put in a 2 up here and a 1/2 out here, wouldn't I then be able to substitute out the 2x minus 1 and just make that a u squared down there, which I think will make life a little bit easier. So we got x plus 1/2 the integral of, and then we'll deal with the x minus 1 in the numerator in a second, u squared plus 2 du. And what is x minus 1 equal to? (2x) is equal to u plus 1, so x is equal to u plus 1 over 2. And so we've got x minus 1, so that ought to be u plus 1 over 2 minus 1. So far good or no? And could I then get a common denominator here? So make this a 2 and multiply by 2. And if I do that, what should I be able to do? I got to be able to pull that 1/2 out here, giving us x plus 1/4 the integral of, and then what do we have here? We have u plus 1 minus 2, which is u minus 1 over u squared plus 2 du. Good or no? And now this looks very similar to the last one we were working on. All right, Molly, what's the question? Or am I just waiting for you to write stuff down? Correct, Nick. I pulled out the 1/2, right? I had u plus 1 over 2 minus 2 over 2. So both of those are divided by 2. So I pulled the 1/2 out. 1/2 times a half gives us a 1/4. So Molly, I multiplied the x minus 1 by 2, but then the 2 goes away because that's the 2 dx. And so that 2 dx right there just becomes the du over here. And I'm just left with x minus 1. And since x was u plus 1 over 2, it's u plus 1 over 2 minus 1. And then I just got the common denominator. Everybody good? Yeah, it's a little complicated. Some of these get pretty messy. So you gotta be extra careful. Okay. So now how are we going to deal with this? Just like the last one, I think Alice said we should split it into 2. Let's do the same. So we got x plus 1/4 the integral of u over u squared plus 2 du minus 1/4 the integral of, what's the other part of it? Minus 1 over u squared plus 2 du. Good or no? And with any luck, this 1/4 the integral of u over u squared plus 2, that's a simple u sub. Right, if u equals, or not u, but v equals u squared plus 2, then dv is 2 du, or 2u du. And so we'll put a 2 and a 1/2, so that'll become a 1/8. And then it's natural log absolute value u squared plus 2. Everybody good so far? And then the other one here, the minus 1/4 of 1 over u squared plus 2, that one looks just like our inverse tangent one that we were dealing with a little bit ago. So we'll have minus 1/4 times 1 over root 2, because that's the square root of 2, times the inverse tangent of u over root 2, all plus our constant. So far good? So all we have to do is what? All we got to do is replace the u's with 2x minus 1s. So what do we end up with? We should end up with, our final answer should be x plus 1/8 natural log of, we could do the absolute value of this thing, even though we don't really need to. It was u squared, so 2x minus 1 squared plus 2 minus 1 over 4 root 2 inverse tangent of 2x minus 1 over root 2 plus our constant. Good or no? And we might note that if we were to expand out this thing up here, in fact, we'll do this just for fun. 2x minus 1 squared is 4x squared minus 4x plus 1, plus the 2 is that 4x squared minus 4x plus 3 that we had at the very beginning, isn't it? All right, so these can get fairly messy. In fact, they can get even worse than that one. But conceptually, everyone okay with that? Okay, let's do another problem. I don't know why I keep having these blank pages in here. Let's take a look at this one. Thoughts on this one? First off, it's a rational function, right? We've already got the denominator factored, but is the degree of the numerator greater than or equal to the degree of the denominator? No, definitely not, right? Denominator's got next to the fifth in it if you were to expand all that out. So let's just do the partial fraction decomposition here. So we've got 1 minus x plus 2x squared minus x cubed over x times x squared plus 1 squared. And so this time, this one's a little different because we've got a linear factor, which means that's just going to get a constant, a over x. But instead of having a singular irreducible quadratic factor, we've got a repeated irreducible quadratic factor. And so just like we did when we had the repeated linear factors, we've got to put a term in there for both of them. So this ought to become plus bx plus c over just the factor, and then plus dx plus e over the factor squared. And if there was, if this was x squared plus 1 to the third, you'd have another one. You'd have fx plus g over x squared plus 1 to the third power. Everybody good with that? Just like we would have had with the linear ones. And we're not going to do any with like with cubics that you can't factor. But if by chance you ever came across one with like a cubic that you couldn't factor, well, you'd have to have an ax squared plus bx plus c. You'd have to have a quadratic factor above it. So anytime you have something that's irreducible, whatever power it is, the thing above it in the numerator has got to be 1 power less than it. Everybody good with that? Hopefully. Okay. So our common denominator is going to be x times x squared plus 1 squared. So the a over x needs an x squared plus 1 squared attached to it. So we're going to clear out all the denominators. And our a is going to get multiplied by x squared plus 1 squared, which I'm just going to write that out now. That should be that, right? That's x squared plus 1 squared. And then our bx plus c is going to get multiplied by both an x. So I'm going to just do the x part of it now. And then in the next step, we'll multiply it by the x squared plus 1. And then the dx plus e just needs to get multiplied by the x. So far, good? And we should get an ax to the fourth plus a 2a x squared plus an a. And then this one is a little bit messier. This is a plus bx to the fourth plus a cx cubed plus a bx squared plus a cx plus your dx squared plus your ex. Nick, I wouldn't multiply it by x squared plus 1 to the third because I only have x squared plus 1 to the second power. I got to get a common denominator. Hopefully you didn't write that down as x squared plus 1 to the third power on yours. I know I was talking about it, but good, Nick, or no? Okay. All right, so now we got to write out our system of equations. So first off, how many x to the fourth do we have on the left? We have 0 of them. So our first equation should be 0 equals a plus b. So we've done those two. Okay. And then our next equation should be for the cubes. So -1 ought to equal c. Oh, that's the only one we've got, right? So that's convenient. And then for the squareds, we've got 2x squareds ought to equal 2a. And then we got plus b and plus d. And then for our x's, we got -1 ought to equal c plus e. And then we got 1 ought to be equal to, looks like the only constant we've got is a. Everybody good with that so far? So we've got 2 of them. If -1 equals c, then what do we end up with for e? E ought to equal E ought to equal 0. So we've got A, we got C, and we've got E. We should be able to find B pretty easily there. If A is 1, then B ought to equal -1. And we have 2A plus B plus D equals 2. So if we plug in the A equals 1, that's 2 equals 2. So we got B plus D is 0. And if B is -1, then that makes D equal to 1. Everybody good there? Any issues with that? Solving that system? Pretty easy. All right, so our integral becomes the integral of A was 1, right? So 1 over x. B, or B and C. B and C were both -1, right? So if B and C were both -1, can I factor the -1 out of that and just put it in between? Make it minus x plus 1 over that first x squared plus 1. I mean, Elon, yeah, theoretically, you could use a calculator and a matrix to solve it, but only if it was a calculator question on the AP test. And then it looks like our, I think, what was our E value? Our D value was 1 also, I think, and our E value was 0. Yeah, so we have plus x over x squared plus 1 squared dx. I think that's what we end up with as our new integral. Does that look good to everybody? Okay. Natural log absolute value x. And then what about this middle one here? How are we going to do that one? How about we separate it into 2 different ones? So minus the integral of x over x squared plus 1 minus the integral of 1 over x squared plus 1, both with dx's on them. I always forget those. And then what about this last one here? If I let u equal x squared plus 1, then du ought to be 2x dx. So let's make this plus 1/2 the integral of du over u squared. Everybody good with me doing the u sub on that? That's u equal to x squared plus 1. And we end up with natural log absolute value of x. Let's see, and then this one right here, this is going to be another u sub. U is going to be x squared plus 1 still, so du is 2x dx, so we need a 2 and a 1/2 on that one. So that's going to be natural log absolute value of x minus 1/2 natural log absolute value of x squared plus 1, and then minus, what's that one? That one's just minus inverse tangent of x. And then this one ought to become, if this is u to the negative 2, that ought to become minus 1/2 u to the negative 1, or minus 1 over 2 times u, which was x squared plus 1, plus our constant. Good or no? Any questions or issues on that one? All right, let's do one more of these. This will be, I think, the last of our partial fractions for now, or at least almost the last of them. You guys want to do this one on your own? Yeah. All right. I'll give you guys about, I don't know, how long do you need for that? About 1 minute. Ready to go. All right. That ought to have been enough time, right? You all are finished. What do you mean no? How are you not finished with that yet? Didn't you go through the steps? Didn't you say, oh, is there an easy u substitution? And you said, yeah, there is. U is equal to x cubed plus 3x, and du is equal to 3x squared plus 3. So this just becomes 1/3 of an integral of 3x squared plus 3 dx over x cubed plus 3x. So 1/3 the integral of du over u. 1/3 natural log absolute value x cubed plus 3x plus your constant. So just because it looks like you should use a partial fraction decomposition doesn't mean that you have to. Always check and see if there's an easy u substitution first. Now, if you'd gone through and done it using a partial fraction decomposition, you would have ended up with same answer, right? But this is a lot easier. So make sure you check for those simple u subs. Everybody good there? Any issues with that? Any questions on that? Everyone good? All right, what should we do with this one? Any thoughts on this one? All right, sometimes it can be helpful, just another trick that you will occasionally be able to use. Sometimes you want to substitute out your entire root function. So if we let u equal root x plus 4, we should be able to do some work rearranging this first to figure out what x is equal, because we'll have to substitute out the x. So what is x equal to? Right, u squared is x plus 4, or x is equal to u squared minus 4. And then from there, we'll be able to figure out what dx is equal to, right? Dx is equal to 2u du. And this ends up giving us what integral? An integral of u times 2u du, right? That's our root x plus 4 dx over u squared minus 4. Everybody good with that? So do you see a good simple u substitution to use here to simplify this one down, or no? Or a v substitution since we've already used u? Probably not. Is the degree of the numerator greater than or equal to the degree of the denominator? Yep, so let's divide. So u squared minus 4 going into 2u squared plus 0u plus 0. And then u squared minus 4 goes into 2u squared twice. So that's 2u squared minus 8. 0u minus 0u is still 0u, and 0 minus negative 8 is an 8. So our new integral should become the integral of 2 plus 8 over u squared minus 4 du. So oftentimes, if we substitute out the entire root, it can give us a nice, fairly straightforward partial fraction integral. And our integral of 2 du ought to be 2u. Careful not to make that a 2x. And then we've got plus 8 times the integral of 1 over u squared minus 4 du. And we had a rule for 1 over u squared minus a squared, or 1 over x squared minus a squared. What was that rule? Should remember it from, I think it was Tuesday that we did that. It ought to be 1 over 2a times natural log absolute value of u minus a over u plus a. Everybody remember that rule? Or if you don't, now you do. And now just replace all your u's with root x plus 4. So 2 root x plus 4. This becomes plus 2 natural log absolute value root x plus 4 minus 2 root x plus 4 plus 2 plus your constant. Any issues with that one? All right. I think that ought to be good for today. So for Weierstrass substitutions, you just draw a right triangle with your angle equal to x over 2. Tangent to that is u and 1. And if you use the Pythagorean theorem, that ought to be 1 plus u squared or u squared plus 1. And so from there, you should be able to see what the sine of x is. You just have to use the double angle formula, right? Sine of x ought to be 2 sine x over 2 cosine x over 2. All right, so you just do your sine, which is u over root 1 plus u squared, and your cosine, which is 1 over root 1 plus u squared. Multiplying together gives you u over u squared plus 1 times your 2. That's how you get the sine x. For your cosine of x, just do 2 cosine squared x over 2 minus 1. That's the double angle for cosine. Plug it in, and you end up getting 1 minus u squared over 1 plus u squared. And then if you want to figure out what your dx is in terms of your du and all that, you can just take the inverse tangent of this and multiply by 2. So you get 2 inverse tangent of u equals x. And then dx is 2 over 1 plus u squared. That's pretty straightforward to get these. But no, these are not on the AP test, Hayden. So I normally teach this because I think it's just good to know for people that are moving on to, higher math and physics stuff in college, engineering. I probably won't use them in much engineering, but if you're doing like pure physics and pure math stuff, you might end up using these some. So just some good substitutions to know that they exist. And so if you were to do this, you just go in and replace the sine of x with 2u over 1 plus u squared. You replace the cosine x with 1 minus u squared over 1 plus u squared, and you replace the dx with 2 over 1 plus u squared du. And it ends up becoming, these will always end up becoming one, or almost always end up becoming one that you need to use partial fraction decomposition for, all in terms of u. And then when you go back and resubstitute at the end, you'd resubstitute out all the u's as tangent x over 2. So I'm not going to give you any problems of these to do. I just want to mention them so you see that they exist in case you ever need them in a future math class, but they're not required material for the AP test. And then yes, Adrian, I will provide you a sheet with everything that you need to have memorized. Yes. And point I usually make about this is, the Weierstrass stuff is great, but don't use Weierstrass substitutions all the time. Like if this one, you could use it. You could have your cosine be your, whatever is 1 minus u squared over 1 plus u squared, and replace the dx and replace the sine squared. And it becomes a little bit of a mess. But if you can just do a simple u sub with u equal to sine of x and du is cosine x dx for something like this, right? In fact, we'll just do this one real quick. If we let u equal sine of x, du ought to be cosine x dx, right? And that ought to give us the integral of du over 1 plus u squared, which is just inverse tangent u plus a constant, or inverse tangent of sine x plus a constant. All right, so the Weierstrass substitutions are great, but if you can find an easier u sub to use, then do it. And then another thing I normally talk a little bit about is the hyperbolic trig functions. And normally I do derivatives with these also, but just be aware that there's these things called hyperbolic trig functions that do exist. This is hyperbolic sine, hyperbolic cosine, hyperbolic secant, hyperbolic cosecant, hyperbolic cotangent, and hyperbolic tangent. I think there it is. There's the last one. And so there's integrals for all of these, and there's some nice little substitutions you can use for these as well. So if you're interested in that at some point, go through and read about those and learn about those and online or something. But it's also not required for the AP test, but I normally talk about those as well. But we'll call it good now for the day with those.